Hi everyone. I'm Muyiwa. I'm a sysadmin with the entity team working on CMP, and my talk is about container management with Kubernetes. An introduction, very important part. So first of all, before we talk about what container management is, we need to figure out why container management. And we will do that by using an analogy. So take, for example, a budding entrepreneur comes up with an idea for $1 million application. And the first thing they do is to develop an MVP as a monolithic application. They deploy that, and surprisingly enough, the application starts gaining traction in the market, and people start using it. And suddenly they realize that they can't scale it as quickly as they would like. So in order to fix that, they hire more developers to help them. The developers come in and they begin to work, but then the developers start to encounter some issues as well because they can't move as quickly as they would like to because everything is in a single application. So a simple way to fix that is to split things into microservices. So that's what they decide to do. What's a microservice? Microservice is an application that is a component of a larger application. So if you have a product that has different features, you can split those features into different microservices that reduce the surface area that developers have to worry about. And when you combine those microservices together, you have your application. And each of those microservices usually communicate through well-defined HTTP APIs, and they can be written in any language. So that gives the developers more freedom to use whatever they are used to or whatever is suitable for the task that they are working on. And all they have to do is just make sure they expose an interface that other microservices can communicate with, and then you have a cohesive application. This helps to solve problems with scalability that large software products encounter. And on the CMP products, which I work on, we have a lot of microservices. This is a good example of what that looks like. On the left-hand side, we have a monolithic application where you just have the user interface, the business logic, the data access layer, and the database all in a single package. So this works for smaller applications, but there's a lot of issues that arise with this when you start moving to larger apps with larger teams. Meanwhile, on the right-hand side, we have a single application, in this case, an e-commerce application, and different features are their own microservice, and they all talk to databases, either the same database or different databases. They also communicate with each other, and together they form the application. So now back to our analogy, you're now developing your microservices application, but when it comes time to deploy, you start having issues. You have issues with complicated networking because you have different microservices running on different hosts. You need to make sure they can all talk to each other. When you move one, you need to reconfigure all the networking and all the rules for how they talk to each other. Dependency management is also an issue because you have all these things running in different programming languages. They might have conflicting dependencies that you have to resolve, and this starts to be a pain. So, instead of you to start reinventing the wheel and trying to fix this, you look into what's available in the market and decide that, okay, I need to use containers, and containers are supposed to help to solve this. So what are containers? Containers are a mechanism for encapsulating applications and their dependencies. They provide a way to isolate an application and all its dependencies into a single package that means that you don't have to worry about what else is running on the host that the application runs on. It also provides greater security for running multiple microservices on the same host. It's also pretty lightweight. However, this talk is not about containers because a couple of months ago I gave another head talk about containers, and that's available on the Headforward's YouTube channel if you want to check that out after this talk. So, we come back to our analogy. Now, everything is in microservices, everything is in containers, we are all looking good. And then we keep on developing the application, keep on developing more microservices, and we run into yet another issue. Managing multiple microservices in containers is difficult. This is because there are a lot of moving parts. There are a lot of things that you need to worry about with deploying, with updating, with maintaining, and all that. You now start developing yet another set of manual tooling to manage this, and it starts getting complicated. But you don't necessarily need to do this because there's a solution for it already. It's a solved problem, and that is where container management comes in. So what is container management, also known as orchestration? It's a means of arranging, coordinating, and managing software containers. It maintains the container lifestyle. It maintains containers across a fleet of services, devices. So you don't have to necessarily worry about your individual servers, but you worry about them as a cluster. And you deploy applications against that cluster, and the container manager figures out where they need to go and how they run on that destination. It also takes care of all the other complexities that are involved in running microservices in containers, such as load balancing, service discovery, networking, etc. And it removes the complexity involved in managing a clustered environment. And it does this by allowing you to declare the desired state of your application, apply that declared state, and then let it go out and set it up the way you have specified. There are a lot of container management platforms available. These are a short list of some of the available options. However, this talk is specifically about Kubernetes. So, what is Kubernetes? That's the logo. Kubernetes is an ancient Greek word for helmsman. And it's an open source project. It's currently under the Cloud Native Computing Foundation, which is a sub-foundation of the Linux Foundation. And it was founded by Google in 2014 based on a similar project called Bug, which they use internally to run Google services. But right now it's developed by thousands of contributors in hundreds of companies all over the world. It's available on all the 3 big cloud providers, so AWS, Azure, and Google, and others all have Kubernetes available if you want to use their hosted solutions. And it's become the de facto standard for building clustered container management solutions in the industry. But what is it really? So again, obviously, it's a container orchestration system because this talk is about container orchestration. And it does all the things that I already said container orchestration systems do. And as well, along with that, it provides a well laid out API, which you can use to extend the functionality that it provides with third-party features. These are some of the features that Kubernetes provides: auto-scaling, self-monitoring, DNS management, load balancing, rollback, centralized logging, extensible architecture, and so on. So now, in order for us to understand how this all works, we need to continue looking at how things will progress with our analogy I was talking about earlier. So say, for instance, you've decided that now that I have my applications running in a cluster, running in containers, in microservices, I need to have them running in a cluster with a container management solution. So what would you do? First of all, you need a cluster. So this is an example of a simple cluster that you could use for a Kubernetes, to run Kubernetes. And here we have 2 different kinds of nodes. You can see the 3 boxes at the top are worker 1 to 3. Those are the worker nodes. And at the bottom there, you have the master node. But what are these? The master node is the Kubernetes control plane. So that is where the services that manage the Kubernetes cluster run. And as you can see, there are 4 of those there. And we are going to get to those later on in the talk. And the worker node is also known as the minions. And these are where your services run. So your actual microservices that you deploy to your cluster run on the worker node. So you probably have way more worker nodes than master nodes in your cluster. So now we want to run an application in a Kubernetes cluster. How do we proceed with that? What are the steps involved? First of all, you need to declare the desired state. So I know my application has X number of microservices. I want to run X number of replicas of each microservice. I want to give this microservice this amount of memory, this amount of CPU. I want to give this other microservice this amount of memory, this amount of CPU. I want to expose this port to this microservice. I want to always restart this other microservice when it dies. Those are the kind of things that you specify, and you specify them in something known as a deployment file. And you specify all these things for each of your microservices, and then you apply that to your Kubernetes cluster. So you apply it to something known as the API server. And the API server is the brain of Kubernetes. It implements a RESTful API and communicates over HTTP, and it has a backend storage where it stores the data that is applied to it, and it usually uses etcd, which is a key value-based store. And you use the clients to talk to the API server, and there are multiple clients available, but the official ones are kubectl, which is a command line client, and the dashboard, which is a web-based dashboard. So now you've defined your state, you've applied it to your cluster. So now you have your API server and you have the client. The client applies the state that you have defined to the API server, and now the API server has to communicate that to other things on the master that will then determine where to host those microservices that you have specified. So now the next thing the cluster does is to determine where to schedule those applications. So, and the Kubernetes control plane has to make decisions about where to schedule your applications. And it makes those decisions using the Kubernetes scheduler. And it schedules those applications as pods. So how does that work? First of all, pods are a basic building block of Kubernetes. So they provide an environment around your containers that Kubernetes manages. So you already have your applications running in containers, but you want to take those containers and run them in your cluster, and Kubernetes runs them in pods. And these pods expose a unique unique IP address for each pod that you can use to communicate directly with it, and that it can use to communicate with other services running in your cluster. A pod can have more than one container in it if it's needed, but for the most part, it's recommended that you have one container per pod. Now, the scheduling decision is made by the kube scheduler, and basically, it has algorithms that it uses to decide where to deploy the pods based on your definition. So if, for instance, you decide that you want to host 2 replicas of a web server, the web server needs to expose ports 443 or port 80 on the host. But we all know that you cannot have 2 services exposing the same port on a single host. So the scheduler knows this, and is going to make sure that it runs each of the replicas on a different host so that they don't conflict with one another. And also things like the memory usage and the CPU usage. So if you specify that you want one of your microservices to use 4 gigs of memory, but you only have one worker that has up to 4 gigs of memory free, it's going to make sure it schedules that pod on that worker and not the other ones that don't have enough memory. So the scheduler is only as good as the information that you give it. So you have to make sure your deployment file is properly, is as explicit as possible so that you give the scheduler enough information to make decisions about where to host your microservices. It tries to spread things as evenly as possible in order to maximize efficiency and utilization of your cluster. And when the scheduler has made these decisions about where to schedule your pods, it then communicates them to the worker nodes using the kubelet. So the kubelet is a Kubernetes agent. It's a process that runs on every server in your cluster. And basically, it manages the pods on that local server. So when the scheduler has decided what to do, it gives that information to the API server. The API server communicates that information to the kubelet, and the kubelet starts up the pod to do what you want it to do. So now this is what our cluster looks like. You have the scheduler there, it makes the decision, it sends it to the API server, and then you have the kubelet running on each of the nodes. The API server gives the information to the kubelet, and the kubelet starts spinning up our pods on the workers. So now at this point, we have a couple of pods running on our workers. Now, we have a bunch of services running, but these services at this point cannot communicate with one another. But like we said, microservices have to communicate with one another in order for your application to work. So how does this work? This works using services. So the idea behind services is each pod has a unique IP address which you can use to communicate with it. But pods are mortal. Basically what this means is they can die at any point in time. And if they die, you lose communication with the microservice that was running there. Even if it gets restarted, there might be a period of a couple of seconds where you lose communication, and that's not what you want. So you want a situation whereby you have an IP address that doesn't change, that you can always use to hit your pods, irrespective of whether there's one pod running or multiple pods running. You need to be able to hit whichever one is available at any point in time. And that is done using services. So services provide the ability to access a pod directly. It load balances the traffic between all the available pods using a static IP address that would never change. And this is achieved using the kube proxy. And it does this by using something called labels. So labels is basically what you think it is. It's a key value pair that you can attach to any of your pods. So I can label my recommendations microservice as app name equals recommendation. That's a label. So every pod that has that app name would have traffic load balanced across them. So this probably gives us a better idea of what that looks like. So now as a client, I'm trying to talk to my app pod, but instead of talking to the pod directly, I talk to the service IP, and then the service IP load balances the traffic to one of the pods. And as you can see, all the 3 pods have the same label attached to them, and that is how the service IP is able to know that these are the pods that I want to communicate with. So going back to our cluster, at this point, we now have the kube proxy, which does the load balancing of the traffic between the pods, and the pods can now talk to each other even across the nodes, and we're able to communicate, and we now have our service up and running. And if we stick an external load balancer on top of that, we can reach it from outside the cluster, and we have our e-commerce application up and running in a cluster in Kubernetes. This is all well and good. However, getting it up and running is just the first stage. You need to also be able to make sure it stays up and it doesn't, when something dies, it gets restarted, and basically it keeps running in accordance with the declared state that you have assigned to it. So how do we achieve this? We achieve this in a Kubernetes cluster by constantly watching the state, the current state, and comparing it with the declared state. So the kubelet, which is the agent that runs on every node, constantly watches everything that is running on that node and reports its state back to the controllers. And these are able to make decisions on whether they need to make changes to what is currently running or not. And the way they do this is through the API server. They get this constant message feedback from the kubelet. So for instance, if you declared your recommendations deployment to say you always want to have 2 replicas running, and maybe for some reason one of the pod dies, you suddenly have 1 replica running, and then the kubelet reports that information back to the API server. The API server sends that report back to the controller, and then the controller decides, we have 1 running, but we should have 2. So I'm going to start up a second one to make sure we have 2 running again. And these are the kind of things that it always does constantly, checking to make sure your cluster always maintains the state that you have specified. So now we insert the controller manager in there, and we have our complete Kubernetes cluster, which is running the way we expect, and it's going to keep running the way we expect as long as we don't do anything too crazy with it. So that's it for the introduction. It's an introduction. So, I try to be as concise as possible, but there's a lot of things that I couldn't cover because I can see I'm already boring a lot of you. So, however, I just want to call out a couple of bonus points that will be interesting to know if you want to, continue researching on this. And obviously, security is a very important one. Whenever you're running anything in production, you always have to be careful about security, and Kubernetes provides a lot of features that allow you to secure your cluster. So you can set up role-based access control so that only people that have specific access can reach your cluster. You can set up network policies so that different pods can only talk to the other pods that they need to talk to, and they can't talk to things that they don't need to talk to, and others. Also, horizontal auto-scaling. It's fine for you to specify your desired state of your cluster. Say, I want to run 2 replicas of this, 3 replicas of that. But what happens if suddenly your website hits the front page of Reddit and you start getting huge amount of traffic? What are you going to do about that? And that's where horizontal auto-scaling comes in. It can use metrics of like CPU usage and memory usage to decide if it needs to spin up more replicas of your microservice in order to meet up with the demand, or scale down if it's not using as much resources as possible. Stateful applications. When you're running microservices, usually your applications are stateless. And what that means is that they don't have any persistent data. They connect to some database somewhere, and they can die and be restarted at will. But there still needs to be persistent data somewhere. And you can have things like databases, queuing systems, stuff like that, which are persistent stateful applications running in your Kubernetes cluster. But that introduces a whole layer of complexity. And a lot of the time, the recommendation is if you don't have to, you don't need to. So you can just run it separately outside of the Kubernetes cluster and expose it to your cluster and have only your microservices running in the cluster. But if you have to, if there's some benefit to running it in your cluster, then you can do that. Another nice feature is with rolling releases. So Kubernetes allows you to make releases, to release new versions of your application without downtime. So it can spin up the new version, make sure it's working, and then spin down the old version and make sure traffic is routed to the new version when the new version is ready. Don't worry, we're almost done. All right, so conclusion. In conclusion, should you now all go out and change all your applications to run in container managers? The answer is probably no. And that's because if you don't have to, you shouldn't. A lot of the time, people jump into like technologies because they are trendy and it's fun and you like tinkering with it. But in production, if you don't have a specific use case for it, it might not necessarily be worth the hassle. For instance, in the CMP project, we have probably over 140 microservices. And we do multiple deployments per day, and it makes a lot of sense to have them running in a cluster container manager. But if you just have your little app with 2 microservices and something, you don't necessarily need to add that layer of complexity. However, if you decide to do, there's a lot of benefit to that, and you're going to make life much easier for yourself. Thank you for listening. Questions? Yes?
Is there always just one master node in the cluster?
No, you can have as many masters as possible. I used one just for a simplified view of what a cluster could look like. But it's usually a good idea to have redundancy in the masters because one could go down at any point. Yeah.
So does that master's API, do they communicate well? Is there a good defined communication between multiple masters?
The masters don't communicate with each other directly. They all use the backend data store, which is the etcd data store. So each API server talks to the data store, and the data store then is clustered and replicated. So each node always has the most up-to-date data. So they don't necessarily need to talk to each other directly. Any other questions?
That's good, sir.
All right. That's it. Thank you.